Hey guys, my name is IBM and today I'm solving 062543 October November 2023. This is IGCSE. You are going to realize that IGCSE papers, especially paper 4, they have become more advanced. As time goes on, they become even harder. So if you're a teacher, you have to be very strict and you have to actually improve on your teaching methods. So without wasting time, I would like to take you to the question paper. So here is the question paper. It is supposed to be 1 hour and 15 minutes. I may take a little more time because I try to explain a lot of things. I would like to also remind you of G as 9.8 instead of 10, as it was in the previous curriculum. So question number 1. Oil of density 0.8 grams per centimeters cubed is poured gently onto the surface of water of density 1.0 grams per centimeters cubed. So the oil is less dense than the water. And they said the oil and the water do not mix. Describe and explain the final position of the oil relative to the water. Because the oil is less dense, it will stay on top. So I'll say oil stays on the surface. Oil stays on the surface, or you could simply say it floats. The oil floats on the water. The reason is because it is less dense. So the explanation, the oil has lower density than the water. So the oil has a lower density than the water. Because oil has a lower density, then it is going to remain on top. An irregularly shaped solid object has a density of 2.7 grams per centimeters cubed. Describe a method to measure the volume of the irregularly shaped solid object. We want to measure volume of an irregularly shaped object. So there are two simpler methods. I will start with the simpler one, which is the displacement can method, where you just fill a displacement can with water and then immerse in the object, so then measure the volume of the water which is displaced. So I think that is the easiest method. So fill a displacement can, or which we call the Eureka can. Fill a displacement can. Fill a displacement can with water and immerse. And immerse the object. And immerse the object, then measure the volume of displaced water in a measuring cylinder. So you must have done that in year 10 in the first term of when you were looking at physical quantities and measurement techniques. Alternatively, the other method could be, I can write it here, you could measure the initial volume, measure initial volume of water. Of course, this is in a measuring cylinder. Measure the initial volume of water in a measuring cylinder. And immerse the object. You immerse the object, then of course the next thing is to subtract the final volume from the initial volume. Subtract the final volume from the initial volume. So that is That is the second method. Okay, so measure the initial volume of water in a measuring cylinder, then you immerse in the object, then subtract the final volume from the initial volume. Actually, subtract the initial volume from the final volume. It is the other way around because the final volume is going to be greater. So subtract the initial volume from the final. The volume of the object is 83 centimeters cubed. Calculate the mass of the object. Of course, we know that density is mass divided by the volume, which means the mass is the density multiplied by the volume. So the density is 2.7. So the density is 2.7 grams per centimeters cubed. Then the volume is given as 83 centimeters cubed. So centimeters cubed has cancelled. So the mass is going to be in grams. So from my calculator, I'll have 2.7 times 83, which is 224.1 grams, or I can write approximately 220 in grams. The figure is a graph that shows how the extension of a spring varies with the load suspended from it. So it's a graph of extension against load. The time the spring constant. So remember from Hooke's law, force is equal to K times X, or K is equal to force over X, where K is the spring constant. So the force is 14 divided by X, which is 4. We don't have units, so we can have our answer either in newtons per centimeters, or we can have it in newtons per meters. So because 4 is in newtons and X is in centimeters, my answer would be in newtons per centimeters. So it's 14 divided by 4. So this is 3.5. So K is going to be 3.5 newtons per centimeter. So I'll write here 3.5 newtons per centimeter. Alternatively, you could say K is equal to force, which is 14 newtons, over distance. I will divide 4 by 100 to change it to meters, so it is 0.04. So this is 0.04 in meters. So 14 divided by 0.04, that would be 350. So K could also be 350 newtons per meter. So you could also have the answer as 350 newtons per meter. On the figure, mark the limit of proportionality and label this point L. So the limit of proportionality is where the straight line stops. So we come here, the straight line stops almost around here. So I'll mark this point L, where the straight line stops. That is the limit of proportionality. The figure shows a car traveling at a constant speed around corner A on a road. On the figure, mark with an arrow the direction of the resultant force acting on the car as it travels around the corner. If the car is moving around the corner, then the force, there is frictional force and there is centripetal force. So the resultant force must be acting towards the center, which is the force that is going to provide the centripetal, that is going to provide motion in the circle, which is the centripetal force. So the resultant force, if this is a circular arc, its center is going to be somewhere around here. So it means the resultant force on the car must be pointing towards this point, towards the center. So this is going to be the arrow. Okay, so the corner B has a smaller radius than corner A. The car travels at the same speed around corner B as around corner A. State how the resultant force changes due to the car traveling around a corner of smaller radius. Of course, for those who are good at physics, remember this force is equal to mv squared over r, even though you are not supposed to use this equation. But your teacher must have told that the force in a circular path is directly proportional to the speed, is directly proportional to the mass, is inversely proportional to the radius. So corner B has a smaller radius, so the force is inversely proportional to the radius. So because corner B has a smaller radius, it means the force is going to be greater. So state how the resultant force changes due to the car traveling around a corner of a smaller radius. So the force increases. The figure shows a boy throwing a ball at an object in a fairground. The ball has a mass of 190 grams and travels horizontally with a constant speed of 6.9 meters per second. Calculate the momentum of the ball. So momentum, small letter p, is equal to mass times velocity. The mass is 190 grams. You divide by 100, it becomes 0.19 kilograms. So this would be 0.19 kilograms times the speed, which is 6.9. So from my calculator, 0.19 times 6.9, that is giving me 1.311. That is going to be either Newton seconds, or it is 1.311 kilogram meters per second. So I'll just write 1.3 kilogram meters per second, or you can write 1.3 Newton seconds. After hitting the object, the ball bounces back. That means there's a change in direction. That means if one direction is positive, the other direction should be negative, since momentum or velocity is a vector quantity. Bounces back along the same straight path with a speed of 51.5 meters per second. The object has a mass of 1.8 kilograms. Calculate the speed of the object after it is hit by the ball. The speed. So I'm going to use just conservation of momentum. So total momentum before collision should be equal to the total momentum after collision. So total momentum before collision is what we have got here. The momentum of the ball is the one which was moving. So total momentum before collision is the momentum of the ball, and the momentum of the object is 0. So total before collision is going to be momentum of the ball, which is 1.3, plus the momentum of the object, which is 0. Then after collision, remember momentum is mass times velocity. So for the ball, the object has a mass of 1.8 kilograms. We don't know its speed, but the ball rebounds. Remember, it bounces back with a speed of 1.5. So its total momentum after, because it bounces back, it is in the opposite direction. So we can say momentum to the right hand side was positive, momentum to the left hand side is going to be negative. So I'll say equals to a negative momentum. The mass for the ball was 0.119 times its speed, which is now 1.5. Then plus the mass of the momentum of the object, which is 1.8 times its speed, which is v. So we shall say that 1.3 plus, we take this one on the left hand side, so that is plus 0.19 times 1.5 is equal to 1.8 times v. So 1.3 plus 0.19 times 1.5. Then I'm going to divide this by 1.8. So this is 0.88. Let me try this again. 0.19 times 1.5 plus 1.3. That is approximately 1.6 equals to 1.8 times v. So v is going to be 1.6 divided by 1.8. 1.6 divided by 1.8, which is approximately 0.8 recurring, or approximately 0.889. So this is going to be 0.89 meters per second. The kinetic energy of the ball is 4.5 joules before the collision and 0.2 joules after the collision. Calculate the change in total kinetic energy of the ball and the object during the collision. Change in total kinetic energy of the ball and the object during the collision. So let's first find the final kinetic energy of the object. Remember, it was initial at rest, so its initial kinetic energy was 0. So the final kinetic energy of the object is going to be, of course, this is a half times mass times v squared. So that is a half. Its mass was 1.8. Then the speed we have calculated is 0.89 squared. Let's see this energy. 0.5 for a half times 1.8 times 0.89 squared. That is 0.71. 0.71 joules. That's the final kinetic energy of the object. Remember, its initial was 0. Then and the kinetic energy of the ball before the collision is 4.5, and after the collision it is 0.2. We want to find the change in total kinetic energy. So total initial kinetic energy was 4.5 joules plus 0, which is 4.5 because the object was at rest. Then the total final kinetic energy is equal to, for the object, for the ball is 0.2 joules plus for the object, which is 0.71, which gives us the total here is 0.91 joules. That's total final kinetic energy. Then the change in kinetic energy, the change in total kinetic energy is going to be equal to 4.5 minus 0.91. 4.5 minus 0.91. So this is giving me 3.59 joules, or approximately 3.6 joules. So that is the change in the total kinetic energy. My handwriting is not good, but it's fine. The lowest possible temperature is 0 Kelvin. 0 Kelvin. State the name of the lowest possible temperature. Of course, 0 Kelvin is called absolute zero. This is called absolute zero. That's the lowest possible temperature on the Kelvin scale. Nitrogen boils at 77 Kelvin. Capture the boiling point of nitrogen on the Celsius scale. Of course, to change from degrees Celsius, from Kelvin to degrees Celsius, we subtract 273. So 77 Kelvin is the same as 77 minus 273 to get the answer in degrees Celsius. So 77 minus 273. So that is negative 196 degrees Celsius. So it means the boiling point is going to be negative 196 degrees Celsius. The temperature of a fixed mass of a gas at a constant volume changes from 300 Kelvin to 400 Kelvin. State and explain in terms of particles the effect on the pressure of the gas. So the temperature has increased. The volume is constant, so the pressure is going to increase. Increase in temperature at constant volume causes increase in pressure. So the pressure increases. So the statement is increased the pressure. Increase the pressure. And then the explanation The particles of the gas, of course, they gain more kinetic energy and move faster, causing more frequent collisions. The particles of gas gain more kinetic energy and move faster. Or we say they gain momentum or they gain more velocity, and move faster, causing a more frequent and forceful collisions. In other words, they exert a greater force or a larger force on the walls. More frequent and forceful collisions of the particles with the walls. So the particles gain more kinetic energy and move faster, causing more frequent and forceful collisions of the particles with the walls. And remember pressure. Let me say since pressure equals force over area, and since pressure equals force over area, greater force means greater pressure. It means greater pressure on the walls. Okay, so because now there's a greater force, we expect a greater pressure. Sample of gas is at a pressure of 120 kilopascals. The volume of the gas is doubled, that is times 2, at a constant temperature. The temperature is constant. Calculate the new pressure of the gas. So of course we know that P times V is going to be a constant, or you could say P1 at constant pressure, PV is equal to constant, or you can say P1 V1 is the same as P2 V2. So let's say the initial pressure is this one, the volume, let's say it is V, and the volume after is going to be twice V because it is doubled. So I'll say pressure is 120 kilopascals times the volume, which is V, is equal to the pressure, which is P2, times the volume, which is twice V. So V cancels out. So it means our pressure P2 is going to be 120 kilopascals divided by 2, which is going to be 60 kilopascals. So the answer here is going to be 60 kilopascals. The figure is a scale diagram of wavefronts of red approaching a gap in a barrier. On the figure 5.1, draw 3 wavefronts after the wave has passed through the gap. So I'll try to measure the wavelength, the distance between the wavelength, and compare with the gap, the size of the gap. From my computer, let me see, measuring from crest to crest. This is approximately about 1.2, and the size of the gap is also about 1.2. So the size of the gap is approximately the same as the wavelength. Therefore, the diffraction is going to be maximum. The wavelength is approximately the same as the size of the gap. So diffraction, we expect maximum diffraction. So I am going to draw maximum bending. So I'll draw the first curve. Of course, the distance between these must be almost the same. It must be the same actually, not almost. Because the wavelength does not change when diffraction occurs. The frequency does not change when diffraction occurs. The speed does not change when diffraction occurs. So for the second one, I must be very careful to ensure that it is almost at the same position. And for the third one, okay. So I have drawn three. Because there are 1, 2, 3 wavefronts, I've drawn three of them. And the curvature here is supposed to be maximum because diffraction is maximum here. However, the guiding points should be you draw three wave crests. The wavelength, the distance between them here is approximately the same as the distance here. So you try to ensure that. And they're supposed to be semicircular arcs, you know. If you have a compass, you just put it at this point here and you draw very nice curves. So that they have, and then you, of course, you open your compass to measure this distance here, and then you put the sharp point at the center here, and then you draw the curves. They will look very beautiful when you use a compass to draw them. Okay, then figure 5.2 shows the same barrier and gap, a wave of blue. Of course, we know that blue is a smaller wavelength, so the wavelength has reduced. A wave of blue approaches this barrier. Draw three wavefronts of this wave before it reaches the barrier. Before it reaches the barrier, blue light has a shorter wavelength. So if this is approximately 1 centimeter, 1.1 centimeter, I will draw the bars, the lines, which have a shorter distance between them. So let me draw this as the first one. So the distance between them must be smaller but equal. So the distance between the wavefronts, this distance here must be smaller. The wavelength must be less. And if the wavelength is less, then the diffraction here is going to be less pronounced. They said, draw three wavefronts after the wave passes through the gap. Now that the wavelength is smaller than the gap, the wavelength is less than the gap size. So the bending is going to be less. So for the first one, there is some slight bending at the edges. But remember, the wavelength does not change, so I must ensure that the distance is almost the same. So I will draw it here, I think, here and around here. So compare these two. Here you have a full curvature where you can even use a compass. Here you cannot draw a compass because the bending is only at the edges. Please ensure that the distance between the wavefronts is remaining the same. I may not be very accurate on my computer, but you can always measure the distance. I'm trying to aim at this distance being the same. Try to erase this. Okay, so that is the diffraction pattern. On the figure, sketch the current voltage graph. That means current on the x-axis, on the y-axis, and voltage on the x-axis. For a filament lamp, of course, for a filament lamp, I think this is easy. Of course, a filament lamp, as voltage increases, the current increases, but a point reaches where the change in current, where the line becomes horizontal, something like that. If you were to sketch the opposite, maybe you have reversed the axis and you have put V here and you have put I here. It is just the mirror image of this. So this curve will go upwards. Something like that. Then explanation, why is the curve supposed to be like that? Of course, as temperature of the filament only glows when its temperature increases, and when its temperature increases, resistance increases. Remember, resistance is V over I. So as temperature increases, resistance increases. So that means the change in current becomes very small because the resistance increases. So I'll say as temperature increases, as temperature increases, resistance increases. Resistance increases. So what does that mean? So more voltage is required for the same increase in current. So more voltage is required for the same increase. So more voltage is required for the same increases in current. I'm saying for a filament lamp, it only glows when temperature increases. Why does the curve become horizontal? It's because as temperature increases, resistance also increases. And when resistance increases, it means you need more voltage to cause a small change in current. So that's why the curves look like that. They are bending, they become flatter on the side of the current. The figure shows an electric circuit. So we see it has diodes in it. Capture the reading on the voltmeter. Of course, current flows from positive to negative, so current is coming like this. So the current is continuing like this. So that means this is not conducting because it has been connected the other way around. So it means all the PD of the power supply is across the 4.2. The PD across this one is going to be 0. V for this one is 0 because it is out of circuit. Because the resistance here is going to be infinite actually. Okay, the PD, because the LED or the diode is reverse biased, it is not conducting, so there is no current here. The current here is going to be 0, which means the PD across this is 0, but the voltmeter is connected across this and this, so it is reading the PD across the upper part. So because the internal resistance here, it is 3 volts and this is 12 volts, so it means the PD across, or the reading of the voltmeter, let me just call it V, is going to be equal to the EMF, which is 12 volts, minus the internal, the PD across the load. Oh, sorry, this one is in this direction and this one is in the other direction, so we just sum them up. So that is 12 plus negative 3, because the other one is connected the other way around. This is positive, this is negative, positive, negative, so it's the other way around. So this is negative 3 volts, this is positive 12 volts if we move in that direction. So this is going to be 12 minus 3, which is 9.0 volts. So the answer here is going to be 9.0 volts. Then calculate the current in the 4.2 ohm resistor. Since I now know the PD across the 2.4 ohm resistor, the current is very easy to get. I is equal to V divided by R. V is 9.0 volts, then R is 4.2. So this is 2.1. So the current is going to be 2.1. The units are amperes. Then determine the current in 2.1 ampere. Of course, this is going to be 0. Why? It is reverse. The diode is reverse biased. So the resistance of the diode is infinity. Resistance R for the diode is equal to infinity, which means current in the diode equals to 0. So since there is no current going through this diode here, it means there is no current through the resistor of 2.0 ohms. So the current in the 2.0 ohms is going to be 0. Remember, the current in the diode is the same as the current in the 2.1 ohms. So since it is 0, this is going to be 0. Then determine the reading on the ammeter. Let's see where the ammeter has been positioned. So the ammeter is here, it is reading the total current. So the ammeter is reading the total current in the circuit, and the ammeter is reading total current in the circuit. So we can find the current into the 4 point. It is the same as the current into the 4.2 ohms, because this one is out of circuit, because the diode, this diode here is not conducting. So this, like this part here, is out of circuit. So the current, the reading of the ammeter is the same as the current through the 4.2 ohms. So I is going to be the same as I in the 4.2 ohms. So the current in the 4.2 ohms was 2.1. So I'll just write here 2.1 amperes. Then calculate the electrical power transferred in the 4.2 ohm resistor. Power. We know that power transferred is equal to I times V. The current is 2.1 and the PD is 9 volts. So we just multiply 2.1 times 9. So that is 18.9 watts, which is approximately 19. So I'll just write here 19 watts. That is 19 watts. The figure shows the electric field pattern around point X. On the figure, draw an arrow to indicate the direction of the force on a negative point charge placed at Y. So if we put negative here, Of course, the field lines are starting from X, so we have a positive charge here. So this is going to be repelled. So it is going to be attracted. So I'll draw an arrow pointing towards the center. Because it is negative, it is going to be attracted. So I will increase the thickness. So I will draw an arrow pointing towards the center. So that is the direction of the force. Because it is negative and at the center, the field lines originate from positive. So at the center where X is, we have a positive. So the negative charge at Y is being attracted. State what is at point X to produce the field pattern shown in the figure. So that is a positive point charge. Positive point charge. It is a positive point charge. A piece of plastic charged positively by friction is charged positively by friction. If it is charged positively, it is because it loses electrons. If it was charged negatively, it would be gaining more electrons. State what charge transfer occurs during this process. So negative charges move out of the plastic. Negative charges move out of the plastic. Negative charges move out of the plastic, leaving behind more positive charges. More positive charges on the plastic. So if the plastic becomes positively charged, it is because negative charges move out, or they are removed. They are removed or they are lost. Move out, removed, or lost. Explain how the structure of an electric conductor differs from the structure of an electrical insulator. Of course, a conductor. Electrical conductor also has free electrons. This one has electrons. And an electrical insulator does not have those free electrons. So because there's just two marks, I will say conductors. Conductors have free and mobile. Chemistry students may want to call them delocalized. Delocalized electrons. Insulators do not have these free electrons. Okay. Then the figure shows the single turn of a coil, the single turn coil of a simple direct current motor, DC motor. Explain the direction of the turning effect as seen by an observer at point O. Okay, I'm going to use a simpler video to show this, a simpler video from YouTube to show the direction of the turning effect. But before we do that, the field lines originate from north to south. So the magnetic field line points in that direction. If you use Fleming's left-hand rule, your first finger points to the left-hand side. Then the current, let's say on the left-hand side, the current is flowing in that direction. On the right-hand side, the current is flowing in this direction. The second finger of your left hand points in the direction of the current. And if you try to do that on your question paper with the first finger pointing to the left and the second finger pointing towards, or it is pointing away from you, you notice that that the thumb is going to be pointing upwards or above the paper. with the first finger pointing away from the first finger pointing to the left, the second finger pointing away from you. If this is your question paper is on the table, the second finger is pointing away from you, the thumb is pointing upwards above the paper. And if you try it on the other side, on the right hand side, with the first finger pointing to the left again, and the second finger pointing towards you for the current, you notice that the thumb points downwards. So you have forces upwards and downwards, which is going to cause a clockwise turn. I can show this on a video. Okay, so in this video, let us assume the current is flowing from positive of the battery to negative. It is flowing this direction, as you can see with those yellow dots. One end is the North Pole and the other end is the South Pole. So if we consider this coil with the current flowing in that direction, it means if you use Fleming's left-hand rule, so the current is flowing in that direction. As shown in the question paper, the current is in that direction. So the magnetic field is from north to right. And basically, we are saying that the coil is going to rotate in that direction, which is actually going to be clockwise, as seen from the side of the bulb using Fleming's left-hand rule. So let's try to see if we use Fleming's left-hand rule on this diagram, what really happens. So the first finger is pointing in that direction represented by white. The first finger, remember, is the magnetic field. The second finger must point in the direction of the yellow, which is the direction of the current. Of course, the thumb is going to point vertically upwards, which is the direction of the magnetic force. And if you repeat the same on the other side, on the right-hand side, we can also repeat the same on the right-hand side. The first finger is still pointing from right to left. The second finger is pointing in the direction of the yellow. The net effect is going to be that clockwise rotation as shown in that simple animation. So having seen that animation, we now agree that the rotation is going to be in the clockwise direction. So I'll simply say clockwise. Clockwise. So the direction of the turning effect is going to be clockwise. And they said explain this. Of course, I said we can use Fleming's left-hand rule. So it means by Fleming's left-hand rule, the force on the left-hand side of the coil is up. The force on the left of the coil is up, and the force on the right of the coil, the force on the right of the coil is down. So the force on the left is up, the force on the right is down, so it is going to cause a clockwise rotation onto the coil. Then the coil is replaced by an otherwise identical new coil with the 3 turns. That is, now we have more turns in the magnetic field. And of course, the force depends on the number of turns in the magnetic field. So if we have more turns, we expect more force. So state how the turning effect compares with the turning effect in Roman 1. Since we have more turns, the force depends on the turns. So we expect that the turning effect is going to be greater. So the turning effect is greater because we have now more wire in the magnetic field. Remember, if we have more wire in the magnetic field, more force is going to be experienced by the wire. A third coil is identical to the coil in 1, except that its resistance is 3 times. If resistance is 3 times, it means the current flowing is going to be a third. The current reduces. And the force, of course, depends on this current. The PD across the coil is the same. If V is the same and the resistance has increased, it means the current has reduced. Remember, V is equal to I times R. That means I is equal to V over R. V has remained the same, but the resistance has increased, the current has decreased. And the turning effect also depends on the current, or the force on the wire depends on the current in the wire. So it means the turning effect is going to be less. The turning effect is less. Then figure 8.2 is a voltage time graph showing the output of a simple alternating current generator. It's a simple AC generator at times t equals to 0 to T1, T2, and T3. The figure is an end view of the plane of the coil of the generator at time t equals to 0. The coil is rotating clockwise. It is rotating clockwise. Draw an end view of the position of the plane of the coil at time t1, include the labels. So at t equals to 0, we are having a vertical, and we see that the voltage is 0. It means the coil is moving, and A is just moving horizontally, say to the right hand side, and B is moving just horizontally to the left hand side. Then at t equals t1, we see that the voltage is maximum. Voltage is maximum when the coil is just horizontal, like this, where one end of the coil is cutting the field vertically downwards, and the other end is cutting the field vertically upwards. Maybe I can show this on a video. Let me check if I can show this on a video. Okay, so in this demonstration for an observer somewhere here, you just see if initially at t equals 0, the coil is just vertical like this. And that means end A is moving parallel, and end D is going to be moving parallel to the left hand side. End A is moving parallel to the right hand side, end A is moving parallel to the left hand side, and this is going to give a zero output voltage. And then after half a cycle, at a quarter cycle, then it rotates in that a quarter a cycle. When it becomes maximum in that position, I will slightly move backwards. Maximum in that position there, A is moving vertically downwards and D is moving vertically upwards. It means the magnetic field is cut at right angles. And if the magnetic field is cut at right angles, it means the induced EMF is going to be greater. So it means A is going to be on the right hand side, and remember B is going to be on the left hand side. So taking you back to the question paper here, A will come here after a quarter a rotation, that is at T1, and B will be here. So what we are going to draw here is just a horizontal, something horizontal like this, with a dot there. Let me increase the thickness. So with A on this side and B on the other side. Okay, then draw an end view of the position of the plane of the coil at T2. So this was T1. Then T2, so this was a quarter, this is a half. half it means half a cycle, it means again we move, we come back where B will be here and A will be here. Then another quarter, when here it means B will be here and A will be here. Then at T2, remember A is here, so it means A, let me see, so we have A here, a quarter cycle, A is here, B is here. Half a cycle, A is here, B is here. 3/4, that is at this point. 3/4, A is going to be here, B is going to be here. Then a full cycle, let me see again. Which is at t equals to 0, we have that. T equals to a quarter, we have that. 3/4, we shall have something like this, where A was at this position. No, half a cycle, we have this, where this will be at half a cycle. This is going to become A, and this will become B. Then 3/4, it now becomes horizontal. A comes here, and B comes here. So where is T2? So T2, again, we come back to the full cycle. A reaches the top and B will be at the bottom. So this is going to be something like this. So A will be at the bottom, at the top. A will be at the top and B will be at the bottom. We shall now come back to the same position as before. That is after one complete cycle. So this is going to be the same as before. I hope I didn't make a mistake in it. Starting from here, this is a quarter cycle. This is a quarter cycle. Then half a cycle, 3/4, then back the same position. So this is going to be correct. Then draw an end view of the position. Draw an end view of the position of the plane of the coil at T3. Include the labels A and B. At T3. T3 is at a quarter, so this is the same as this point here, and that is 3/4. I think this is what I had done already here. This is t equals to 0. It is horizontal at t equals to a quarter. Then this was t equals to a half a period. This was t equals to 3/4 of a period. This was t equals to a full period. So the cycle has repeated. So T3 is 3/4. So it is going to be just horizontal with A on the left hand side and B on the right hand side. So this is going to be just like this. With A on the left hand side and B on the right hand side. Okay. This is quite a hard paper, but regardless, we move on. For each application of radioactive isotopes, state and explain which type of radioactive emission is suitable and suggest an appropriate half-life for the isotope. Household smoke alarm. I think for household smoke alarm, we use alpha particles. Alpha particles are used for household smoke alarms. The type of radiation is alpha. Of course, alpha particles have a very high half-life. So why do we use why are alpha particles? Of course, these ones are highly ionizing. because the smoke alarm is going to rely on high ionization. Alpha particles have a charge of positive 2e, so they are highly ionizing. Highly ionizing and not very penetrating. They're highly ionizing and they are not very penetrating. I think the half-life of alpha particles ranges between 10 to around 500 years. So I will just quote a value, say 400 years. So you can quote any value between 10 to 500 years. Measuring the thickness of aluminium, of course, measuring the thickness of aluminium, because alpha particles cannot penetrate through paper, so we can't use them to measure the thickness of aluminium. But beta particles can penetrate paper and only to be stopped by a thick material of aluminium. So here we can use beta radiation or beta particles. Why? Absorption depends on the thickness of aluminium. Their absorption depends on the thickness of aluminium. Beta particles can be absorbed by a thick material of aluminium. Of course, the half-life of beta particles varies, so I can give any number of years. I can give, say, 4 years or 2 years. This can be any number of years. Any number. The half-life of beta particles can be any number of years, so I can say 2 years. Then lead has the highest nuclear number of the stable isotopes of lead. Explain why lead-214 is radioactive. There's lead-208 and lead-214. Just look at the nuclear number, which determines the proton number. So it's like lead-214 has many more neutrons, which makes it extremely more unstable. So it has, because this is 214, the other one is 208. So this one has too many more neutrons. It has um, too many neutrons, and of course decay reduces the number of neutrons, and decay reduces the number of neutrons. That's why it is going to be very radioactive, because decay reduces the number of neutrons. So since a lead-214 has many more neutrons, it will decay to reduce the number of neutrons to gain stability. State two different sources of background radiation. Of course, background radiation have many sources, but the most common ones are radon gas. We have radon gas in the air. We have rocks, building materials, rocks or buildings or building materials. We have you can find background radiation in foods, food or drinks. We can find background radiation in what we call cosmic rays, and so many others. All those are going to cause background radiations. Then state what is represented in space physics by the symbol H naught. Of course, this is Hubble's constant. Hubble's constant or Hubble constant. Write down the equation that defines h naught in terms of the speed of the galaxy moving out from the Earth and its distance. Of course, we know that v is equal to h naught times d. The numerical value of h naught is 2.2 times 10 to the power of minus 18. State the unit of h naught. Of course, this is per second. Hubble's constant is per second because um, if h naught is equal to v divided by d, v is in meters per second and the distance is in meters, so you only remain with the per second. So the answer is per second, or you can write s power minus 1. Then use the value of h naught to determine an estimate for the age of the universe. So the age is time, which is distance over speed. The distance is d, the speed is equal to h naught times d, which means d cancels out, you remain with 1 over h naught. So this is 1 divided by 2.2 times 10 to the power of minus 18. They want the answer in seconds, so I will just say 1 divided by 2.2 exponent minus 18. So this is 4.55 times 10 to the power of 17. 4.55 times 10 to the power of 17 seconds. And lastly, state when cosmic microwave background radiation was formed and where we detect it coming from. Of course, these are believed to have been formed right from the Big Bang, right at the creation of the universe. They are detected in all points in space. So these are believed to have formed shortly after the Big Bang. So I'll say believed to have formed shortly after the Big Bang. Shortly after the Big Bang, or after the universe was formed. And of course, they are detected in all points in space. They are detected in all points in space. They are detected everywhere. These are the microwave background radiations. So they are detected everywhere in space. And they are believed to have formed shortly after the Big Bang, or they are believed to be remains of the Big Bang. I think that marks the end of this paper. They are detected in all points in space. Okay. Until next time, I would like to stop here. Bye bye.